Thank you, Thierry. Hello, everyone, and thank you very much for your time to participate to this webinar. My name is Cosmin Vatra. I'm a physics engineer, and I'm responsible with CFD Simulations in the Swiss company Aseptconn. Aseptconn is a leading supplier of components, products, software systems, and engineering services for liquid sterile technology. We are acting in pharma, biopharma, and other critical industries. We combine our innovative products with worldwide leaders' top products like Merck KGaA, Darmstadt, Germany, Steriflow, ITT, and of course with our engineering expertise. We know that mixing in tanks and reactors is really a very important process for the industries like pharma, biopharma, food and bev, and chemical. It looks to be simple and easy manageable, but in practice it has big challenges and leads to a high number of failures and issues. I would like to give you just some examples of issues. Under and oversize the mixer power, non-homogeneous suspensions and emulsions, high mixing and heating times, foaming, cell damaging, especially for bioreactors, mixing problems at low liquid levels, process transfer and upscale failures, overheating of sensitive and explosive products. When we are designing a mixing system, we have a lot of questions like, did I choose the right mixer model? Using of a simple mixer it's enough, or I need to add a high share mixer? I need to use a top or a bottom mounted mixer. Which motor power I need? I need 2 kilowatts or maybe 10 kilowatts motor. Which tank design is suitable for my application? Horizontal or vertical design? Dished or conical, or maybe tulip shape? Which dimensions ratios are better? So we have too much variables in the mixing process, a wide range of existing substances having different physical and chemical properties combined with different mixer design and different tank design leads to practically infinite possibilities of mixing situations. Decision is a lottery without the prediction of the process parameters. So my question is, what's happening if we are losing to this lottery and the mixing process fails? It's a simple but heavy answer. The system should be redesigned. And worse, in most of the cases the old tank could not be modified and the new one should be built. And here starts the nightmare. Redesign and rebuild costs, delays, penalties. If the cost to redesign and rebuild the tank are high, having an order from 10,000 till some hundreds thousands of euros or dollars, the production delay for 1 to 3 months is highly affecting the profit forecast by creating an income loss up to millions of euros or dollars. We know this because we have asked some of our customers from pharma industry, and they can manufacture products with values from around 10,000 euros per batch up to 500,000 euros per batch. They can produce 1 to 3 batches per day, so they will not be happy to lose 1 to 3 months of production. Now, let's see how can CFD helps us. I think that we can understand very easy from this logical decision diagram. If there are available mixing experimental data done on an identical geometry, the project is safe. If there are available experimental data but performed on a different geometry, we can choose to complete them with CFD simulations for the real geometry. In this case, the project will be safe. If we do not complete them with CFD simulations, there is just a small risk. If previous experimental data are not available, we can compensate with data prediction by using CFD simulations. In this case, we will have data predicted by CFD. The decision will be done based on clear data. The results will be a safe project. If we do not run CFD simulations, The decision will be based on feelings or limited to some previous experience. The risk level will be high. We can say that CFD transforms an empirical risky decision into a safe one based on clear data. I am very happy that many important key decision managers are understanding and recommending the use of the CFD simulations. The company Merck KGaA Darmstadt from Germany provides scientists and engineers with best-in-class lab materials, technologies, and services. They are dedicated to making research and biotech production simpler, faster, and more successful. Mr. Olivier Marchal, Europe, Middle East, and Africa Customer Application Director from Merck KGaA, Darmstadt, Germany, was very happy to transmit his vision to all the webinar participants. He said that CFD simulations are true enabler for peace of mind, ensuring the right tank geometry and mixer selection with performance and efficiency in mind. This is probably the best data and science-based approach to address these increasingly demanding mixing process challenges, embedding and delivering quality by design. Very nice words. Thank you very much, Mr. Olivier Marchal. Let's go now to Italy, to Techninox, one of the biggest pharma system producers of fully automated processing plants for liquid forms for pharmaceutical, biotech, cosmetic, and food and beverage industries. Mr. Franco Miglioli, Techninox General Manager and co-owner, a very experienced engineer, was excited to share with us his thoughts. He said that CFD is a great tool for predicting the process parameters. It is complementary to our engineering experience and helps us to choose the right design and technical solution. We are considering to use it by default for all the projects. Now let's take a look at the standard CFD simulations services that we at Aseptconn are offering for pharma industry. I will present an example for each one. The Mixing Basic package is our fundamental CFD service that gives a characterization of the mixing capacity of a specific geometry formed by a tank and a mixer in relation with the main liquid used for production. We can support multi-use or single-use installations. In our example, we have studied the mixing in a Mobius 3000 power mix system. We have simulated the mixing for different liquids. Here you can see some of the results for two different solutions, water and a viscose solution of poloxamer. We have performed power analysis, flow pattern analysis, and turbulence analysis. Here are the characterization curves for this system with 3000 liters of water, power and energy dissipation rate depending on mixer angular velocity, also the power number curve versus Reynolds number. Another standard service is the powder suspension option for studying the mixing of a non-dissolving powder into the main liquid. The main target of the study is to understand the powder behavior in relation with the main liquid and to perform an analysis of the homogeneity and mixing time. In this example, the application is the mixing of calcium carbonate pharma-grade powder. Here you can see some results. Analysis of Stokes number reveals that the powder will easily follow the liquid streamlines. The powder will have the tendency to go out of the vortex region, creating their regions with higher concentration than in the vortex region. Anyhow, the volume fraction contours show a good homogeneity. The suspension time as a function of mixer angular velocity is obtained. Comparing with the experiment, CFD has the advantage to predict the volume fraction in all the points, not only in the sampling ones. Here we have the powder dissolution option for studying the mixing of a dissolving solid, which can be in form of powder or granules, into the main liquid. The main target of the study is to understand the powder or granules behavior in relation with the main liquid and to obtain the dissolution time graphic. The example's application is the dissolution of pharma-grade salt granules in purified water. The questions are: which is the granule's dynamic behavior? Could big granules affect the mixer head? Which is the dissolution time? The simulation revealed that the salt granules behavior is to go outside the vortex region towards the tank wall. The mixer will not be affected by the granules swarm. We have obtained the graphic of dissolution time in function of dissolution percentage. Let's go now to the option Mixing two liquids. This is for studying the mixing of a second liquid ingredient into the main liquid. The main target of the study is to obtain the mixing time. The example is from a model validation with the experimental data done for Merck KGaA Darmstadt, Germany laboratory. The application is a mixing of sodium chloride solution in the liquid having 2 centipoise viscosity and 1,200 kilograms per cubic meter density. The question is, which is the mixing time needed to reach 95% homogeneity, which is called also T95. You can see the movie of the mixing process. The mixing time is precisely obtained by considering 9 virtual sensors placed in the tank in different positions, up, middle, down, combined with left, center, right positions. A graphic is plotted for every sensor, giving information about more points than laboratory measurements can offer. Heating-cooling option is for studying of the heating or cooling of a liquid by circulating a heating or cooling agent in the mantle while mixing. The target of the study is to obtain minimum and maximum temperatures, heating or cooling necessary energy, heating or cooling time. The example is from a study performed for Techninox. The application was heating of ethanol, a liquid with explosion risk from 5 Celsius degree to 22 Celsius degree. The question was, which is the maximum temperature of the heating water in order to avoid ethanol heating over 26 Celsius degrees, and which is the heating time? From the CFD simulations results that it is not possible to heat the agent from the mantle more than 26 Celsius degrees. The ethanol will reach the desired temperature of 22 Celsius degrees in approximately 19 minutes with a very good homogeneity. The customer considered that 90 minutes are too long for the production timing and decided to change the heating solution. This is one of my favorite simulations, bioreactor and fermenter option. The target of this kind of study is to perform an analysis of gas holdup of Kl, the oxygen mass transfer coefficient, of A, the interfacial area concentration, and of Kla, the volumetric oxygen mass transfer coefficient. The example is from an internal evaluation of the oxygen mass transfer for different Sparger models, different positions, and airflows. Bubble dimensions play a crucial role in bioreactors and fermenters' fluid dynamic. Small bubbles are spherical and have small vertical velocity, while the large ones become elliptical and go with high velocities. This is why we are performing a separate evaluation and simulation to determine the bubble dimensions generated by the Sparger. Then we are keeping into account the coalescence and the breakage phenomenon happening inside the tank. You can see the distribution in the bioreactor of bubbles of different sizes and the final gas holdup. After obtaining the information about the air bubbles, we can simulate and obtain the oxygen mass transfer coefficient. the interfacial area concentration, and the volumetric oxygen mass transfer coefficient. You know that simple tricks could make our life easiest in many cases. So we are looking for indirect calculations and simulations that could give important information about some phenomena that are very difficult or costly to be simulated directly. This is the case of Vortex air option that is very useful for the applications of mixing of substances that have foaming behavior. For these substances, the vortex formation should be avoided because it is leading to a strong foaming. The target is to answer to the following questions. Will the tank geometry be favorable to vortex formation? Which will be the maximum mixer angular velocity for which is not a bearing vortex? It is important to understand that the success of the CFD simulations could be guaranteed only by a complete expertise chain. In our case, we have chosen the CFD software ANSYS Fluent, which is really amazing, for which the software level expertise is assured by ANSYS and CADFEM. They are experts in the general equations and models for physical and chemical phenomena. They are organizing professional trainings, webinars, and conferences. At Aseptconn, we are covering the process expertise level, which is very important. We take care of specific process equations and models, customized parameters and functions. We are performing validation of the models with the research literature, experimental validation of the models, and data interpretation. Thank you for your attention. Visit us on aseptconn.ch and don't forget to follow us on LinkedIn for the next webinar about AsepSoft, our new software for P&ID process design and simulation.